So we talked earlier about there's different types of galaxies out there. There are elliptical galaxies, spiral galaxies, barred spirals, lenticular, irregular. But one of the things to keep in mind is that as we look at distant galaxies, we are looking back at those galaxies as they were a long time ago. We talked about look-back time. And we talked about the cosmological horizon, the fact that we cannot at some point see any galaxies beyond, for instance, 13.7 billion light years, because beyond 13.7 billion years or so, our universe was not in existence. So galaxies, looking way back, they look a little more chaotic. And so, for instance, this is kind of this first set right here are just young galaxies from the Big Bang, which would be 0 billion years ago, up to, what, about 3.5 billion years. They kind of look like this. And elliptical galaxies, looking at elliptical galaxies far away, so they're looking back in time, versus elliptical galaxies now. They kind of evolve, and this is generally what we see elliptical galaxies as now. Spiral galaxies and irregular galaxies. So we can kind of now think of, after the Big Bang, after kind of actually something called a relatively short period of inflation, where space and time was expanding faster than the speed of light, we end up with kind of this, the universe is this homogeneous blob, and it's relatively warm. So if we take one kind of box of that, the new universe, it looks like this. It's all uniform. And so then actually, as it cools down, it cools down, and as it's expanding, it can allow for then gravity to go ahead, and those particles can form atoms, and then those atoms can go ahead and form compounds. And I guess I shouldn't say that. Early on, we just had hydrogen was the first atoms to be formed. And then we got heavier and heavier elements as stars got to go ahead and do their thing in their cores. But this process kind of reminds me of fragmentation. I don't know if you remember back when we talked about how a molecular cloud or a giant molecular cloud can have multiple stars form in the same kind of pile. So also what we're looking at here is kind of the web of, it's not really necessarily a web, but a web of material in the early universe that actually we're going to have clusters of galaxies form. So just focusing on one little, like, dense core, so to speak, that is actually large enough to ultimately make a galaxy of stars. We call that a protogalactic cloud. I think we looked at that term before when we looked at the Milky Way, the formation of the Milky Way galaxy. So at the time of those first generation of stars in these galaxies only had access to the most basic elements, those being hydrogen and helium and a little bit of lithium. So once it cooled, then we could go ahead and within these protogalactic clouds get a galaxy's worth of stars to be formed. Well, an assortment of stars can be formed, those early stars, but a large number of these massive stars were formed. And remember, massive stars live their lives quickly, and then they give back quickly, and they end their lives in supernova events. So that's kind of the early universe and the galaxies in the early universe. So these galaxies, some of them were spinning and some of them weren't. So galaxies that were rotating, these disks, these blobs of stars that were rotating, then needed to, that angular momentum that was associated with rotation needed to be conserved. So actually rotation is going to be key in kind of the disk dominating in our spirals and barred spiral galaxies, and basically no disk in our elliptical galaxies. That's kind of what you see from left to right. So what you're looking at is the Hubble tuning fork kind of display of the different types of galaxies. Of course, these E over here are ellipticals. Then we have the S for spirals, the SB for barred spirals, and perhaps we could, these are kind of almost segueing to lenticulars, where the tuning fork prongs meet. So our protogalactic cloud will kind of look at two different scenarios. Is there spin or is there no spin? And actually, the top scenario from left to right is showing basically no spin. And can you see where this bottom scenario is showing a little bit of spin? Now, these are protogalactic clouds, much larger than a giant molecular cloud that we've talked about earlier when we talked about the formation of clusters of stars. So bottom line, can you see where if we do have spin on the cloud, rotation on the cloud, then, and we kind of talked about this with the formation of our solar system just within our own star, that as it kind of flattens out into a disk sort of shape, we, that angular momentum, that spin needs to be conserved, and it'll spin faster and faster. And we'll end up with a disk dominating, and we'll have spiral arms. And then up here where there's no rotation, we end up with, actually we can have stars form in this protogalactic cloud, but the stars then will be in a galaxy, in an elliptical galaxy. So not only spin, but also there's a difference in density between these ultimately two types of galaxies. Elliptical galaxies on the top, spiral galaxies on the bottom. As it turns out, elliptical galaxies, their stars are pretty darn dense, and we think then their protogalactic cloud was pretty darn dense, which just means per a volume there was a relatively large amount of stuff. Compare that to kind of the sparse nature of a rotating protogalactic cloud that gives us a spiral galaxy. So those two things, rotation and density, are a factor in getting these two major types of galaxies. So here actually in just the fall 2012, they have, I read recently on the internet that they think they have found a candidate for the most distant galaxy, and it's a red elliptical galaxy. And now maybe as we talk about redshift, it kind of makes sense that the farther galaxies are from us, they have a faster recessional velocity, and so they are going to, any visible light we see is actually going to be shifted clear over here to the red. So to finish that thought, the distance between us and this red elliptical galaxy is 13.3 billion light years. So there you go. One of the things I'm not emphasizing much this semester, but I think it's interesting that galaxies actually do interact with each other, and we see that in many different cases up there when we look at galaxies. And so here you're seeing two galaxies interacting, and actually their interaction between their disks and their nuclei actually is causing these stars to kind of be spewed out. And so, not so surprising, you might imagine that before, earlier on in the expansion process, when galaxies were closer together, we think that probably there were more collisions than there are today. And I don't think I have a slide on it, but as we understand it, actually, there are, what I start to say is the Andromeda Galaxy is actually on a collision course with the Milky Way, but I think we're going to be fine with that too. So here are some, kind of looks again pixelated, but an assortment of galaxies that were very early galaxies. This again is that pair of galaxies we looked at before, and actually galactic collisions is one of those ways that we can take a giant molecular cloud and we can get some little dense cores to start and stimulate star formation. So this is kind of showing, it almost looks like a dance, doesn't it? But remember that galaxies hang out in what we call galaxy clusters. So, you know, they are gravitationally interacting with each other, and they can do that perhaps to the point of intersecting, and that's kind of what you're seeing here. So as you can kind of imagine, clear over here to the right, when we have such a collision or interaction, we end up with some sort of kind of odd, sort of irregular galaxy. Which, by the way, sometimes students will ask, well, now, if each of those galaxies, you know, start over here from left to right, if each of those galaxies had a supermassive black hole in their centers, what happens to those black holes? And I guess, as I understand it, they do merge and become one, and that merging process can release a lot of energy, too. So I think we looked at this view before where these are actually, this is a cluster of galaxies, and these galaxies are generally elliptical galaxies. And we do generally see elliptical galaxy clusters as being very rich. And this is kind of scary, isn't it? If we kind of look for the hot spots of these elliptical galaxies, we can see where it appears that a lot of these elliptical galaxies have merged to form a large one in the center. Again, clusters of galaxies are gravitationally associated with each other. Okay, this kind of talks again about how, well, this is just talking about a starburst galaxy that was formed because of an interaction with another galaxy, and they tend to kind of use up their matter kind of quickly. Again, kind of looking at kind of the disk of, I think what you're looking at is, this is the disk of a galaxy looking in the X-ray region of the electromagnetic spectrum. And remember when we talked about the Milky Way galaxy, we said if you have stars in the disk that are going supernova, then actually that material is kind of ejected above and below the disk in halo region, and that's kind of what you're seeing there.